two galaxies are colliding in a slow-motion ballet of destruction. This is the Antennae Galaxies, a place where the normal rules of the cosmos no longer apply. We are about to journey into the heart of this celestial wreckage to uncover 50 of its strangest secrets. You will discover everything from stellar ghosts catapulted into the void to the invisible grip of dark matter itself. What kind of stars are born from such violence? And what happens to the supermassive black holes at the center of the chaos? What do you believe is the most profound result of a collision on this scale, reaching far into the emptiness of space? Two immense streamers of cosmic material stretch for hundreds of thousands of light years. These are the tidal tails, the colossal antennae that give this galactic collision its name. But these are not solid arms. They are ghostly rivers, vast streams of stars, gas, and dust that were violently torn from the hearts of the two original galaxies. This is the first and most profound evidence of the collision, a scar written across the cosmos. The force responsible for this cosmic sculpting is gravity itself. As the galaxies first swung past each other, their mutual gravitational pull did not simply tug politely. It created a differential force, a tidal force, that was far stronger on the near side of each galaxy than on the far side. This unimaginable stress stretched the galaxies, pulling them apart like cosmic taffy and flinging billions of stars out into the intergalactic void. These long, luminous tails are not just debris, they are a fossil record. By studying the age and composition of the stars within them, astronomers can read the history of the impact, tracing back the timing and the ferocity of that first close passage. They are the enduring signature of a gravitational dance that began millions of years ago, a permanent monument to the moment everything changed. Within these vast tidal tails and the mangled galactic cores, something extraordinary is being forged. The collision has ignited a firestorm of creation, giving birth to over 1,000 superstar clusters. These are not ordinary stellar nurseries. Each one is a colossal city of stars, so densely packed and brilliant that they represent some of the most intense star-forming regions ever witnessed in our universe. Imagine a single cluster containing the mass of 1,000,000 suns, all crammed into a relatively tiny pocket of space. The gravitational turmoil of the two galaxies smashing together has compressed enormous clouds of hydrogen gas to an unbelievable density. This is the trigger, a cosmic pressure cooker where gas collapses under its own weight, igniting a frenzy of stellar birth on a scale that dwarfs anything in our own tranquil Milky Way. These superclusters are more than just a temporary spectacle. They are essentially infant globular clusters, the ancient spherical swarms of stars that orbit mature galaxies like living fossils. We are witnessing, in real time, the formation of the very structures that will grace this merged galaxy for billions of years to come. Their brilliance is so intense that the ultraviolet radiation pouring from their hottest, youngest stars causes the surrounding clouds of gas to fluoresce, painting the chaotic galactic landscape with glowing, ethereal colors. This violent cosmic collision is not just about destruction. It is a monumental factory of new suns, seeding the future of an entirely new galaxy. Yet this brilliant firestorm of creation is held within an invisible cage. The galaxies are not just colliding, they are embedded within a colossal, unseen structure, a halo of dark matter that vastly outweighs all the visible stars and gas combined. We cannot see it, we cannot touch it, but its presence is betrayed by gravity itself. The immense speed of the stars swirling within the tidal tails and the chaotic cores defies explanation. If only the visible matter were present, The entire system should have flown apart long ago. The fact that it holds together, that the stars move so quickly, points to one inescapable conclusion. A tremendous amount of hidden mass is providing the gravitational glue. Astronomers map this phantom halo through a phenomenon called gravitational lensing. The collective gravity of all this dark matter acts like a giant, invisible lens in space, subtly bending and distorting the light from even more distant galaxies behind it. By studying these tiny, telltale distortions, scientists can trace the dark matter's distribution, revealing a vast, spherical halo that envelops the entire colliding system. This collision is not just reshaping the visible universe, it is also churning this unseen ocean of dark matter. As the galaxies merge, their individual dark matter halos are also slamming together. Current theories suggest that dark matter, which does not interact with itself or normal matter except through gravity, may be flung outwards, creating an even more extensive, diffuse halo around the newly formed galaxy. This invisible architecture ultimately dictates the final form of the merger, a silent, dominant presence guiding the violent ballet of light. Amid this chaos of creation, some stars are not being born, they are being violently evicted. These are the hypervelocity runaway stars, stellar projectiles flung out from the Antennae Galaxies at speeds so immense they can never return. They are the cosmic shrapnel from a galactic explosion, catapulted on one-way journeys into the emptiness of intergalactic space. How does a star achieve such a staggering velocity? The answer lies in the extreme environments forged by the collision. One primary mechanism is a gravitational slingshot within the superstar clusters we just explored. In these densely packed cities of stars, complex gravitational dances are the norm. Sometimes, a tight binary star system will wander too close to the cluster's supermassive black hole. The black hole's immense gravity can violently disrupt the pair, capturing one star into a tight orbit while flinging the other away at a phenomenal speed, like a stone from a sling. This three-body interaction transforms the star into a solitary projectile, its trajectory a straight line out of the galaxy forever. Another, even more explosive launch mechanism involves supernovas. Imagine a binary system where two stars are locked in a mutual orbit. If one of them goes supernova, the sudden, asymmetric blast can literally kick its companion star, sending it careening through space at hypervelocity. The runaway star then plows through the thin gas of intergalactic space, its own stellar wind compressing and heating the material ahead of it. This creates a brilliant, bow-shaped shockwave, a glowing trail of ionized gas that marks the star's frantic escape path. These stellar fugitives are more than just a spectacular side effect. They are direct evidence of the unimaginable forces at play in the colliding antennae, proving that in this cosmic wreck, even the stars themselves are not safe from being thrown into the void. While some stars are being violently expelled, others are just beginning their lives, hidden deep within colossal structures that defy human scale. Towering over the chaotic landscape of the Antennae Galaxies are immense pillars of cold molecular gas and dust. These are not gentle spires. They are the foundational architecture of star birth, and they make the famous pillars of creation in our own Eagle Nebula look like mere hillocks. Stretching for dozens of light years, these dark, brooding columns are the nurseries where the next generation of suns is being assembled. They are born from the very same turmoil that is reshaping the galaxies, vast reservoirs of raw material compressed and sculpted by the titanic forces of the collision. But what is carving these monumental structures? The very stars they are helping to create are also responsible for their destruction. Intense radiation from the brilliant, hot, newborn stars in the surrounding superstar clusters acts like a cosmic sandblaster. This powerful stellar wind batters the vast clouds of gas, eroding them away and leaving behind only the densest, most resistant knots of material. These knots, shielded from the onslaught, become the towering pillars we observe, their shapes a direct map of the ferocious environment that surrounds them. Yet within these dark, dusty shelters, new stars are igniting. The pillars are not passive sculptures, they are active construction sites. The same radiation pressure that is eroding the pillars from the outside is also compressing the gas within their dense cores. This triggers gravitational collapse, pulling matter inward until the temperature and pressure at the center becomes so extreme that nuclear fusion sparks to life. A new star is born, hidden from our view by the very cocoon that created it. How can we possibly see these infant suns? Our eyes and ordinary telescopes are blind to this process. The thick dust shrouds the visible light completely. It is only through the infrared eye of observatories like the Hubble and James Webb Space Telescopes that we can peer inside. Infrared radiation, with its longer wavelengths, penetrates the dust like sunlight through a fog, revealing the glowing protostars deep within their dense cores. These pillars are therefore both a testament to creation and a chronicle of destruction, temporary monuments in a cosmic cycle where the death of one structure gives birth to the stars of the future. Hidden within the brilliant firestorm of the antennae, a different kind of power is at work. Scattered across the colliding galaxies are mysterious, intensely bright beacons, each one pouring out staggering amounts of X-ray energy. These are the ultraluminous X-ray sources, or ULXS for short. A single one of these cosmic lighthouses can outshine a million suns, but all of that energy is concentrated into a single, piercing point of X-ray light. This is a profound mystery. A typical stellar mass black hole, the remnant of a collapsed star, has a strict limit to how brightly it can shine as it consumes material. This is known as the Eddington limit, a point where the outward pressure from the radiation it emits balances the inward pull of its gravity, preventing it from eating faster. Yet these ULXS are shattering that limit, shining hundreds or even thousands of times brighter than they should be able to. How is this possible? Astronomers are investigating two compelling theories to explain these overachieving powerhouses. The first theory points to a long-sought, elusive cosmic beast, the intermediate mass black hole. These would be the missing link in black hole evolution, far larger than a single dead star but smaller than the supermassive monsters at galactic centers. An intermediate mass black hole with the mass of thousands of suns would have a much higher Eddington limit, allowing it to consume vast amounts of material and naturally shine with the incredible X-ray brilliance we observe. The second theory suggests we are seeing something just as strange. Perhaps these are ordinary stellar mass black holes that have been given a cosmic feast. The galactic collision has stirred up immense reservoirs of gas, and a black hole could find itself at the center of an unprecedented deluge of material. It would be gorging itself, entering a special super Eddington state. In this frantic feeding frenzy, the infalling gas is so dense and chaotic that it can trap its own radiation, allowing the black hole to temporarily violate its own limits and shine with an unnatural, ultraluminous glow. The Antennae Galaxies, rich with the raw materials of the collision, provide the perfect environment for both scenarios. We could be looking at a population of rare, middle-weight black holes, or we could be witnessing common black holes behaving in an extraordinarily uncommon way. These brilliant X-ray points are a direct challenge to our understanding of how matter behaves under the most extreme gravitational conditions, proving that in this cosmic collision, even the fundamental rules of physics are being pushed to their breaking point. These brilliant X-ray beacons are not the only markers of stellar death in the chaos. Scattered like ghostly bubbles throughout the Antennae Galaxies are the expanding shells of ancient supernovas. These are the remnants of stars that have already lived their lives and met a spectacular end. We cannot see them with ordinary telescopes, for their visible light has long since faded. Instead, we detect their faint, persistent echo through the radio waves and X-rays they emit, a whisper of a long-vanished cataclysm. Each one of these shells is a cosmic chemical factory. When a massive star explodes, the unimaginable violence of its death forge fuses atoms together in a final, furious act of creation. It is within these expanding fireballs that the raw elements of the universe are cooked into something more complex. The star synthesizes heavy elements like iron, oxygen, and silicon, then blasts them outward at nearly the speed of light, seeding the surrounding clouds of gas and dust with these fundamental building blocks. This process of cosmic enrichment is the most important legacy of a supernova. The pristine hydrogen and helium gas that filled the early universe could only form simple stars. It took these stellar explosions to create the diverse palette of elements necessary for everything else. The iron in your blood, the oxygen you breathe, the calcium in your bones, all of it was forged in the heart of a dying star and scattered across space by a remnant just like these. In the Antennae Galaxies, where supernovas are likely occurring with startling frequency, this enrichment process is happening at an accelerated rate. The interstellar medium is being flooded with these heavy elements, creating a far richer, more complex environment for the next generation of stars and planets. Any rocky worlds that form around these new suns will be built from this pre-enriched material, increasing the chances that they might one day develop the chemistry required for life itself. These ghostly shells are more than just tombs. They are the fertile ground from which future solar systems will grow. Deep within the fiery core of this galactic wreck, two invisible monsters are locked in a cosmic duel. These are the supermassive black holes, the original hearts of the two spiral galaxies, each one containing the mass of millions, perhaps even billions, of suns. They are no longer resting at a comm center. They are now partners in a frantic orbital dance, circling one another in a binary system that is the ultimate legacy of the collision. Their immense gravitational pull carves out a zone of pure chaos in the very center of the merger. Stars that venture too close are not simply pulled into orbit. They are whipped and slung on wildly unpredictable paths, like marbles spun on a cracked plate. This gravitational maelstrom prevents the black holes from slowing down and merging quickly. They are caught in a stalemate, a dizzying waltz where they transfer energy to the surrounding stars, kicking them out in the galactic halo or onto bizarre, looping trajectories. This intricate dance, however, cannot last forever, as they shed their energy by disrupting the orbits of these stellar bystanders. The black holes spiral ever closer. Their orbit tightens over millions of years, a slow but inevitable descent toward an unimaginable finale. When they finally do collide, the event will be among the most violent the universe can produce. The merger will not create a flash of light, but something far more subtle and profound. A tsunami in the fabric of space-time, itself known as gravitational waves. These are ripples that travel at the speed of light, stretching and compressing everything in their path. While this final merger is still far in the future for the antennae, observing this binary system gives us a front row seat to a process that shapes galaxies across the cosmos, a slow motion preview of a cataclysm that will one day shake the very foundations of reality. Even the beautiful deaths of stars are not spared from the chaos. Drifting through the turbulent seas of the antennae are the rogue planetary nebulae, the luminous, glowing shrouds of dying suns. In a quieter galaxy, the final breath of a star like our own sun would be a relatively serene event, a gentle puff of its outer layers forming a perfect, glowing sphere around its core. But here, nothing is allowed to be serene. These cosmic butterflies are being violently displaced from their stellar nurseries, their delicate structures stretched and twisted by the immense gravitational tides and the relentless pressure from surrounding stellar winds. Their normally symmetrical shells are warped into bizarre cometary shapes, with long, glowing tails streaming behind them like banners in a gale. This distortion is a direct imprint of the environment, a visible record of the forces tearing through the galaxy. But these displaced nebulae are more than just battered relics. They have become invaluable tracers for astronomers. Each one acts as a single, brilliant point of motion, a glowing tag on an ancient star. By charting the positions and velocities of these rogue nebulae, scientists can map the invisible currents of stellar migration within the merger. They reveal how entire populations of older stars are being stirred and redistributed by the collision, painting a dynamic picture of the great stellar scramble underway. These beautiful, distorted ghosts are therefore telling a dual story, one of a star's quiet end and the galaxy's violent rearrangement, all written in their ethereal, shifting light. The same violent forces that warp stars and gas are also twisting an invisible cosmic skeleton. Deep within the antennae, the galaxy's magnetic fields are being stretched and amplified into bizarre new shapes, creating an invisible architecture of immense power. We cannot see these fields with our eyes, but their presence is revealed by the faint, polarized radio waves that stream from the collision. This polarized light acts like a cosmic compass, its orientation directly tracing the lines of magnetic force woven through the chaos. Before the collision, these fields were likely ordered, following the graceful spiral arms of the original galaxies. Now they are anything but orderly. The titanic forces of the merger have acted like a giant, chaotic mixer, churning the fields and dragging them along with the swirling currents of gas. They are compressed in some regions, intensifying their strength, and torn apart in others, creating a tangled web of magnetic filaments. This distorted magnetic framework is far from a passive bystander. It actively shapes the evolution of the entire system. These fields channel the flow of tenuous gas, guiding it along invisible highways toward the densest regions where new stars are born. They also act as colossal particle accelerators. Charged particles, like protons and electrons, become trapped by these magnetic lines, whipping back and forth until they approach the speed of light, becoming the cosmic rays that constantly bombard interstellar space. Most profoundly, these magnetic fields exert a pressure that works against the force of gravity itself. In a cloud of gas collapsing to form a star, the embedded magnetic field can provide crucial support, slowing the collapse and ultimately influencing the final mass and number of stars that are born. The chaotic magnetic tapestry of the antennae is therefore a fundamental player in the drama, an unseen hand that both guides the construction of new suns and governs the acceleration of matter to its most extreme energies. These superstar clusters are not just growing from within, they are also consuming their neighbors. In the dense stellar environment of the antennae, a process of cosmic cannibalism is likely underway, where the largest and most massive clusters are capturing and absorbing smaller clusters and isolated field stars. This is not a gentle process, but a violent gravitational takeover. A dominant cluster, with its immense collective gravity, acts like a deep well in spacetime. When a smaller, less massive star cluster passes too close, it cannot escape the pull. It is drawn in, its stars gradually stripped away and added to the larger cluster's population. Even individual stars wandering through the chaos can be captured, pulled from their solitary paths, and forced into the bustling stellar city. This gravitational consumption dramatically alters the fate of the cannibal cluster. With every capture, it grows in both mass and physical size, becoming an even more dominant force in the galactic landscape. The process is a direct echo of what happens on a much larger scale when galaxies themselves merge. This relentless accumulation of mass through mergers is thought to be a key mechanism for building the most massive globular clusters we observe orbiting ancient, quiet galaxies. The brilliant superclusters we see in the antennae today may be the youthful precursors to those ancient, dense swarms of stars. They are not just forming, they are actively building themselves up by devouring the competition, growing into the gravitational titans that will endure for billions of years after the final collision dust has settled. At the very heart of this collision, hidden from our eyes, burns a furnace of unimaginable power. The galactic core of the antennae is one of the most luminous objects in the local universe, but its brilliance is not in the light we see. It radiates an overwhelming flood of infrared energy, a deep thermal glow that betrays the frantic activity concealed within. This is the signature of a luminous infrared galaxy, a LIRG, a class of objects defined by their incredible hidden energy output. The source of this brilliant heat is the collision itself. As the two galaxies have intertwined, their gravitational dance has acted like a cosmic funnel, channeling immense rivers of gas and dust directly into their shared central region. This material piles up, creating a deeply obscured, incredibly dense environment where star formation is not just encouraged, it is forced into overdrive. The core is a pressure cooker of creation, where countless new stars are igniting in a ferocious burst of activity. So why can we not see this directly? The same vast clouds of dust that provide the raw material for these new stars also act as a nearly perfect shield. Visible light, with its short wavelengths, is completely absorbed by these thick dust lanes. The energy from the brilliant young stars, however, does not simply vanish. It is absorbed by the dust grains, heating them until they themselves begin to glow, re-radiating all that captured starlight as infrared radiation. It is a transformative process, where the fury of visible light is converted into a deep, warm haze. Observing this core with an optical telescope would be like trying to look through a brick wall, while an infrared telescope peers straight through the dust to see the glowing embers within. This hidden heart is therefore the true engine of the merger, a place where the galactic collision has concentrated its creative force into a single, shrouded, and intensely luminous inferno. This galactic firestorm is not contained. The immense energy generated within the antennae is now punching holes in the galaxy itself, launching vast winds of superheated material out into the void. These are not gentle breezes, but colossal outflows, a form of intergalactic pollution on a staggering scale. The primary engines behind this exodus are the very forces of creation and destruction we have already witnessed. Thousands of supernovae are exploding in rapid succession. each one acting like a titanic piston, driving shockwaves through the surrounding gas. Simultaneously, the fierce stellar winds from the hottest, most massive newborn stars pour forth a constant, high-speed stream of charged particles. Together, these phenomena create an overpressure, a cosmic blowtorch that the galaxy can no longer contain. Enriched gas and dust, now laden with heavy elements forged in stellar furnaces and supernova blasts, are violently ejected. This material does not simply fall back. It escapes the galaxy's gravitational pull entirely, streaming outwards at speeds of millions of miles per hour. These galactic winds carry a cargo of oxygen, carbon, iron, and silicon, the very elements that are the building blocks of planets and life. They inject this enriched material directly into the intergalactic medium, the vast, near-empty space that separates galaxies. For aeons, this cosmic wilderness was a pristine desert, composed almost entirely of primordial hydrogen and helium. The Antennae merger is now seeding it with the ingredients for complexity. This pollution is a fundamental game changer for the future of the cosmos. When the next generation of galaxies begins to form, condensing from the gas in this region of space, they will not start from scratch. They will be born from pre-enriched material, giving them a head start in forming rocky planets and, potentially, the chemistry for life. The violent death of two spiral galaxies is therefore fertilizing the cosmic landscape, ensuring that their legacy will be woven into the fabric of galaxies yet to be born. Beyond the brilliant clusters and dark pillars, the Antennae Galaxies hold more subtle, ghostly signatures of their violent past. Wrapped around the central chaos are faint, arc-like streams and vast, diffuse shells of ancient stars. These are not the product of new creation, but the forensic evidence of a slow-motion dismantling, the lingering echo of a smaller galaxy being systematically torn apart and consumed. These stellar streams are the galactic equivalent of breadcrumbs, tracing the orbital path of the victim galaxy as its stars were stripped away by the immense tidal forces of its larger companion. Each shell is like a ripple in a pond, marking a moment when the smaller galaxy swung through the core of the larger one, losing another layer of its stellar body with each pass. The process is a gravitational autopsy, revealing the sequence of the feast. How can we be sure of this interpretation? The proof lies in the powerful alliance of observation and simulation. Astronomers create incredibly detailed computer models of galactic collisions, programming in the laws of physics, and then letting the digital dance unfold. When they simulate a merger between a large spiral galaxy and a smaller companion, the resulting simulation consistently produces these exact same faint streams and shells. The virtual universe recreates the ghostly structures we see in the real antennae. This match is more than just confirmation, it is a time machine. By tweaking the simulation until its output perfectly mirrors the actual observed structures, scientists can rewind the cosmic clock. They can determine the precise masses of the original galaxies, the angle of their initial approach, and even the number of close encounters they have already experienced. These stellar ghosts provide a timeline of the collision, a step-by-step history written in the scattered remains of a galaxy that no longer exists. This silent testimony allows us to witness an event that unfolded over hundreds of millions of years, revealing the patient, relentless nature of gravity's appetite. This frantic stellar production line is leaving a unique chemical fingerprint on the entire system. The gas and stars of the Antennae Galaxies are displaying peculiar abundance patterns, a strange elemental signature that sets them apart from more sedate galaxies like our own Milky Way. In a quiet galaxy, chemical enrichment is a slow, gradual process, like a forest growing and recycling its nutrients over centuries. But here, it is a rapid, explosive event, more like a volcanic eruption fertilizing the land in a single, violent moment. The key lies in the types of stars being born and dying in such quick succession. The collision has triggered a frenzy of star formation that heavily favors massive stars. These are the stellar titans, the ones that live fast and die young. In their brief lives of only a few million years, they burn through their nuclear fuel at a prodigious rate, fusing hydrogen and helium into heavier elements like oxygen, neon, and magnesium deep within their cores. Then, they end their lives in spectacular supernova explosions, scattering these newly forged elements far and wide into the surrounding gas. This creates a very specific chemical pattern. The interstellar medium of the antennae becomes unusually enriched with the elements that massive stars produce, like oxygen, while elements that come from longer-lived, lower-mass stars, such as iron, have not had as much time to accumulate. It is an imbalance, a snapshot of a system that is chemically out of sync. This makes the antennae a unique living laboratory. By measuring these chemical quirks, astronomers can watch the process of galactic chemical evolution happening in real time, accelerated to a breathtaking speed. They can trace how the products of one generation of stars are immediately incorporated in the next, observing the universe's recipe for complex matter being written right before our eyes. The same invisible halo of dark matter that binds the antennae together also warps the space around it, creating a cosmic mirage. This colossal mass, both visible and unseen, acts as a gravitational lens, a natural telescope forged by gravity itself. The phenomenon occurs because the immense collective gravity of the Antennae Galaxies curves the very fabric of spacetime around them. When light from a distant galaxy, far behind the collision, travels through this warped region, its path is no longer straight. It bends, following the curves of this gravitational well on its journey to our telescopes. The result is not a blur, but a precise and often bizarre distortion of reality. The light from that single, distant background galaxy can be stretched into a long, luminous arc, a perfect Einstein ring, or even split into multiple, identical images surrounding the antennae. It is like looking through a giant, rippled piece of glass at a candle flame, seeing its light smeared and duplicated. This gravitational mirage is far more than a cosmic curiosity. It is one of the most powerful tools astronomers have for mapping the invisible. The specific way the background light is distorted provides a direct, measurable map of the total mass causing the bending, including the dominant dark matter. By analyzing the intricate shapes of these distorted arcs and multiple images, scientists can perform a kind of cosmic tomography. They can reconstruct the precise distribution and density of the dark matter halo enveloping the entire collision. This allows them to see the invisible scaffolding that dictates how the galaxies merge and how the tidal tails were flung so far into space. Every distorted image is a snapshot of gravity's true face, revealing the hidden architecture that holds this entire celestial wreck together. This constant stellar violence produces a sky alive with sudden flares. The Antennae Galaxies are a stage for transient events, sudden flashes of light that appear and fade like cosmic fireworks. These are not just more supernova, but a whole spectrum of brilliant eruptions, including classical nova, where a white dwarf star steals just enough material from a companion to ignite a runaway nuclear explosion on its surface. In a quieter galaxy, such an event would be a rare and notable spectacle. Here, they are commonplace, a direct consequence of the frantic star formation churning out countless stellar pairs destined for explosive relationships. The sheer density of stars increases the probability of these violent interactions, turning the entire merger into a flashing warning beacon in the cosmos. Dedicated monitoring campaigns keep a constant watch on this celestial light show. Telescopes around the world and in space take repeated images of the antennae, night after night, hunting for any new point of light that was not there before. When one is found, an alert is sent out across the astronomical community, triggering a frantic rush to observe the event with every available instrument, from radio telescopes to X-ray observatories. Each flash is a precious data point, a fleeting laboratory. A nova's light curve, how it brightens and fades, reveals the precise physics of the surface explosion. A supernova's spectrum acts as a forensic tool, dissecting the elemental composition of a star we never knew existed until the moment it died. By studying these sudden flares, astronomers are piecing together the life cycles of stars born in the most extreme of nurseries, answering fundamental questions about how often they explode, what they leave behind, and how their explosive deaths differ from those in more peaceful galactic neighborhoods. Every flicker of light is a message in a bottle, a brief, brilliant story of a star's final moments, sent to us from the heart of a galactic wreck. The elegant, swirling pinwheels that once defined these galaxies no longer exist. Their beautiful spiral arms and orderly rotating disks have been shattered, warped beyond recognition by their relentless gravitational tides. In a normal spiral galaxy, stars travel on calm, circular orbits around a central hub, like cars on a vast cosmic racetrack. But here, that predictable structure has been completely randomized. Stars are no longer following neat paths. They are flung onto wildly eccentric, chaotic trajectories, crossing and recrossing the galactic center in a dizzying three-dimensional scramble. This gravitational randomization is the fundamental process that erases the past. As the stars are stirred and scattered, the delicate, flat disk structure of the original spirals is irrevocably broken down. The galaxies are losing their distinct identities, their stellar populations mixing into a single, more amorphous cloud. This is the violent birth of a new shape, a more elliptical structure. Unlike the flat, rotating disk of a spiral, an elliptical galaxy is a football-shaped swarm of stars where motion is more random, with stars pulsating in and out in a complex, disordered dance. The antennae are caught in the act of this transformation, their broken disks a testament to the fact that gravity is not just a force of attraction, but also a force of chaos, capable of dismantling entire galactic architectures and forging something entirely new from the stellar wreckage. These cosmic fireworks are also the source of an invisible, high-energy downpour. The Antennae Galaxies are among the most prolific cosmic ray factories in the nearby universe, constantly flooding space with atomic particles accelerated to nearly the speed of light. These are not rays of light, but subatomic shrapnel, primarily protons and atomic nuclei, that have been stripped of their electrons and hurled across the cosmos with unimaginable force. You are being gently peppered by these particles right now, but in the antennae, the downpour is a deluge. The primary engines for this relentless acceleration are the very same forces of stellar death and birth we have already witnessed. When a massive star explodes as a supernova, the blast wave expands for thousands of years, acting like a colossal, slow-moving piston. This shock front plows through the surrounding interstellar gas at millions of miles per hour, creating a turbulent, magnetized barrier. Charged particles become trapped in this magnetic maze, bouncing back and forth across the shock wave. With each crossing, they gain a little more energy, like a tennis ball being volleyed with increasing force between two relentless rackets. Over centuries, this process, known as Fermi acceleration, can boost a single proton to energies far beyond anything humanity's most powerful particle colliders can achieve. At the same time, the powerful stellar winds from the hottest, youngest stars create their own smaller shock fronts, adding to the chaotic mix of natural particle accelerators. The result is a galaxy-wide network of cosmic ray production, where the constant violence of the merger ensures a steady supply of raw particles and the immense energy needed to launch them. These high-energy particles then thread their way through the galaxy, guided by its tangled magnetic fields, carrying with them a record of the most extreme processes at work in this celestial collision. Amid this spectacle of brilliant suns and violent explosions, an unseen population of faint, cold objects may be lurking in the shadows. These are the brown dwarfs, the so-called failed stars of the cosmos, and the Antennae Galaxies could be teeming with them. A brown dwarf forms just like a star from the collapse of a cloud of gas and dust, but it never gathers enough mass to cross a critical threshold. Its core never becomes hot and dense enough to ignite the sustained nuclear fusion that defines a true star. It is a celestial ember, a perpetual adolescent that glows only with the faint, residual heat of its violent birth, then slowly cools into darkness over billions of years. Spotting these objects is one of astronomy's greatest challenges. They are incredibly faint, emitting most of their light in the infrared part of the spectrum, and they are often lost in the glare of their brilliant stellar siblings. Detecting them requires the most sensitive infrared telescopes, like the James Webb Space Telescope, to pick out their dim, warm signatures against the chaotic background of the merger. If they are present in the vast numbers that some theories suggest, these hidden dwarfs could be a significant piece of the puzzle. They represent a form of mass that is nearly invisible to our telescopes. While they could not account for the immense gravitational pull of dark matter, a vast population of brown dwarfs could contribute to the unseen mass within the superstar clusters, influencing how these dense cities of stars move and hold themselves together. Their collective gravity would act as a subtle glue, helping to bind the clusters and affecting the orbits of the brighter, more massive stars. Their formation in this chaotic environment is also a compelling mystery. The collision produces a wide spectrum of gas clouds, from those massive enough to create superstar clusters to countless smaller, lower-density clumps. Many of these smaller clumps may lack the critical mass to form a true star, instead condensing directly into these failed stars. The antennae could therefore be a factory not just for brilliant suns, but for a shadow universe of dim, cooling orbs, a hidden demographic that quietly shapes the dynamics of the most luminous structures in the collision. Gravity in the Antennae Galaxies does more than just destroy and create. It also composes a silent, intricate music. Across the chaotic expanse, certain orbits begin to resonate, creating a hidden architecture of stability and chaos. This is the phenomenon of gravitational resonance, a subtle but powerful force that acts like an invisible hand, shepherding stars and gas into specific zones. Imagine a child on a swing, where a small, perfectly timed push on each cycle builds into a massive, soaring arc. In the galaxy, this push comes from the rhythmic gravitational tugs of massive structures, like the orbiting cores of the two galaxies or the dense superstar clusters. when the orbital period of a star or a cloud of gas is a simple fraction of the period of a larger perturber. Their gravitational interactions sync up. This synchronization can either protect or destroy. In stable resonant zones, objects are gently guided into safe, repeating paths, like a cosmic roundabout. In unstable zones, the repeated rhythmic tugging adds energy to an orbit over time, violently ejecting the object or sending it plunging toward the galactic center. This celestial choreography has a direct and visible impact on the landscape of star formation. Vast rivers of gas can be herded by these resonances, funneled directly into the dense cores of superstar clusters, providing the fuel for even more intense stellar birth. Conversely, these same forces can clear out other regions, creating empty voids where star formation is effectively shut down. The brilliant firestorm of the antennae is not a uniform blaze, but a patchwork of intense light and profound darkness, its pattern dictated by the unseen, rhythmic beat of gravity's silent song. The Antennae Galaxies are a cosmic chimera, a beast that reveals a different face through every lens we point at it. If you were to look at it with only your eyes or an ordinary optical telescope, you would see a beautiful but incomplete portrait. You would witness the glitter of countless suns and the dark, obscuring lanes of dust, a snapshot of the stellar population. But this visible light view is just one layer of the truth. To see the full creature, we must observe it across the entire electromagnetic spectrum, a task that requires a fleet of specialized observatories working in concert. In the quiet radio waves, the galaxies transform. The brilliant stars fade in the background, and the entire structure becomes outlined by vast, cool reservoirs of atomic hydrogen gas. These are the raw materials, the primordial fuel for star formation. And the radio view shows us how this fuel has been stretched and contorted into the magnificent tidal tails by the collision. It is a map of potential, the unseen ocean that feeds the fire. Switch to the infrared, and the opaque dust lanes that block our optical view suddenly begin to glow with their own deep, warm light. The hidden heart of the merger, shrouded in optical images, burns brilliantly here. The infrared eye pierces the dust, revealing the intense, hidden starburst in the core and the faint heat of countless newborn stars still wrapped in their dusty cradles. This is the thermal signature of the collision's creative fury, the energy of creation made visible. Then there is the X-ray vision, which reveals a universe of violent extremes. The calm tapestry of stars is replaced by a sky peppered with brilliant pinpoint beacons. These are the ultraluminous X-ray sources, binary systems feasting on gas, and the million-degree remnants of supernova explosions. The X-ray view shows us where matter is being heated to its absolute limit, where gravity is at its most intense, and where the most energetic processes are relentlessly at work. Each wavelength band is like a different instrument in an orchestra. The optical view provides the melody of the stars. The infrared adds the deep rhythm of hidden heat and dust. The radio waves contribute the bass line of cold gas, and the X-rays crash in with the symbols of high-energy violence. Only when we listen to all of them together do we hear the full, symphonic story of this galactic collision. The true antennae is not the beautiful optical image, nor the eerie radio map, nor the fiery X-ray sky. It is the sum of all these layers, a multi-wavelength phantom whose complete form exists only when we learn to see with more than light. The invisible dance of the supermassive black holes may soon ignite the most brilliant beacon in the cosmos. This is the potential for triggered quasar activity, a phase where the galactic core transforms from a hidden furnace into a light so intense it can outshine every star in the galaxy combined. For this to happen, the black holes need a consistent and massive fuel supply. The ongoing collision provides exactly that, acting as a cosmic delivery service. Vast rivers of gas, stripped from the galaxies and funneled inward by the same gravitational chaos, are now pouring into the central region. If even a fraction of this gas spirals down into the accretion disks surrounding one or both of the black holes, the result would be cataclysmic. As the gas is compressed and heated to millions of degrees in its death spiral, it would blaze with a light that spans the entire electromagnetic spectrum. This is the essence of a quasar, a quasi-stellar object, whose pinpoint brilliance can be seen across the universe. The entire shrouded, infrared luminous core of the antennae could tear open, its dust blown away by the tremendous radiation pressure, revealing a naked, searing eye of light. But is this a permanent new state for the galaxy, or merely a fleeting moment in its long life? This brilliant quasar phase is almost certainly a temporary one, a short, spectacular finale to the merger process. The very power that creates the quasar also seals its fate. The intense radiation and powerful particle jets blasting from the black hole act like a cosmic hurricane, blowing the surrounding gas and dust clear away. This shuts off the fuel supply, starving the black hole and causing the brilliant beacon to slowly dim back into obscurity. The galaxy would then settle into its final form, a quiet elliptical galaxy with a dormant supermassive black hole at its heart. The Antennae Galaxies offer us a front row seat to this potential ignition, a chance to witness the triggering of a quasar not as a distant, ancient event, but as a dynamic process unfolding in our cosmic backyard. Even the debris of this galactic wreck is giving birth to new suns, far from the chaotic cores, out in the vast, lonely expanses of the tidal tails themselves. Astronomers have made a startling discovery. Isolated pockets of star formation are flickering to life, creating stellar nurseries where none should logically exist. These are not stars that were simply flung out during the collision. These are brand new stars, being born in the darkness of intergalactic space. The long streams of gas and dust that were torn from the galaxies have not remained uniform. Within these colossal rivers, turbulence and gravity have worked their subtle magic. Denser clumps of gas have begun to coalesce, pulling in more material from their surroundings. Over millions of years, these isolated pockets have grown massive enough and dense enough to cross the critical threshold. Their own self-gravity has overcome the internal pressure, triggering a collapse that ignites nuclear fusion. New stars are flaring into existence, not within a galaxy, but within the debris field it left behind. These stellar orphans are a population that belongs to neither of the original spiral galaxies. They are citizens of the tidal tail itself, born into a life of cosmic solitude. Their very existence challenges our traditional definitions of what a galaxy is and where star formation can occur. It proves that the creative force of a galactic collision is so immense that it can spill over, seeding even the most desolate regions of space with the potential for new light. Any planets that form around these stars would have a truly alien sky, a view dominated by the two receding galactic bodies from which their raw materials were once violently expelled. The violence of the Antennae's black holes may not be confined to the present. Etched across the radio sky could be the ghostly footprints of their past fury, enormous structures known as relic radio lobes. These are the cosmic equivalent of a thunderclap that has long since faded to a whisper, vast bubbles of superheated plasma that were inflated by jets erupting from the black holes millions of years ago. When a supermassive black hole is actively feeding, it can sometimes channel some of the infalling material into two powerful narrow beams, or jets, that shoot out from its poles at nearly the speed of light. These jets, made of charged particles and magnetic fields, plow into the intergalactic medium for hundreds of thousands of light years, inflating gigantic, balloon-like structures on either side of the galaxy. These lobes are filled with a soup of relativistic particles that spiral along magnetic field lines, and as they do, they emit a faint but distinctive radio signal. That signal is the key to finding them. In the antennae, astronomers are searching for just this kind of faint, diffuse radio glow surrounding the collision. Spotting these relic lobes is incredibly difficult. They are no longer being actively fed by jets, so their emission is weak and spread over a colossal area, making them far dimmer than the brilliant point sources and star-forming regions that dominate other wavelengths. It requires the most sensitive radio telescopes, like the Very Large Array, to patiently map the sky, looking for the subtle, extended haze that betrays these ancient bubbles. If they are found, they would rewrite the history of the merger. They would prove that the central black holes were once far more active and powerful than they are today, unleashing energies that shaped not just the stars around them, but the very intergalactic space for vast distances. These fading radio echoes are a direct window into a more violent chapter of the collision, a time when the black holes roared with a power that shook the cosmos. Every burst of light from the Antennae Galaxies carries a hidden message, a complex barcode of color that astronomers can decipher. When this light is stretched out into a full spectrum, it reveals not a smooth rainbow, but a dense forest of sharp lines, both bright and dark. Each one of these spectral lines is a unique fingerprint, an unbreakable signature of a specific element like hydrogen, oxygen, or iron. A bright emission line appears when a cloud of hot gas glows at a precise color, while a dark absorption line is etched in the spectrum when cooler gas in front of a light source steals that same specific color. This forest is far more than just a chemical inventory. The exact position of each line in the forest holds the key to understanding motion. If a line is shifted slightly toward the blue end of the spectrum, it tells us that particular cloud of gas is rushing toward us at incredible speed. A shift toward the red means it is flying away. By reading these subtle shifts for thousands of lines across the entire galaxy, astronomers can create a fantastically detailed three-dimensional map of the chaotic flows within the merger. They can trace individual rivers of oxygen flowing inward to feed the starburst, or identify vast shells of hydrogen expanding outward from supernova blasts. The width of a line reveals the temperature and density of the gas that created it, with broad, fuzzy lines indicating turbulent, hot regions and sharp, narrow lines pointing to colder, calmer pools of material. This spectral forest is therefore a living data stream, a real-time chronicle of the entire system's physics, allowing us to see not just where the gas is, but precisely how it is churning, heating, cooling, and moving in this grand celestial collision. This invisible halo of dark matter may be far more complex than a simple, smooth sphere. For decades, astronomers have modeled it as a vast, diffuse cloud, a gravitational cushion that holds galaxies together. Yet the violent merger of the Antennae Galaxies is challenging that elegant picture. The latest, most sophisticated computer simulations of this collision produce a startling result. They suggest that the dark matter halo, stirred by the same gravitational chaos that is shredding the visible galaxies, might not be smooth at all. Instead, it could be a turbulent sea, filled with invisible clumps and dense substructures, all orbiting within the larger halo like phantom islands in a ghostly ocean. This is the concept of an asymmetric dark matter distribution, a fundamental shift in how we envision the universe's hidden scaffolding. How could we possibly detect these invisible clumps? The evidence is indirect, but compelling. It comes from studying the precise motions of the stars and gas we can see. If the dark matter were perfectly smooth, the gravitational pull on these visible objects would be consistent and predictable. But astronomers are finding subtle anomalies, tiny gravitational tugs that cannot be explained by the smooth halo model alone. It is as if the stars are responding to the presence of unseen, massive objects moving through the dark matter background. These gravitational ripples hint at a hidden landscape of immense density variations. The implications of a clumpy dark matter halo are profound. It would mean that dark matter has its own rich and complex internal dynamics. As the two original dark matter halos collided and merged, their individual substructures would have interacted, some being torn apart, others surviving as distinct massive clumps. This behavior would provide crucial clues about the very nature of dark matter particles themselves. If they are capable of clumping on such small scales, it would rule out certain theoretical models and point toward specific, more complex particle properties. The Antennae Galaxies are therefore more than a cosmic wreck. They are a natural laboratory for probing the architecture of the invisible universe, forcing us to question whether the dark side is a placid sea or a churning, chaotic realm of its own. This grand collision has ignited a self-sustaining cosmic engine, a furious cycle of matter that redefines the very meaning of galactic life and death. Within the antennae, the universe is recycling itself at a breathtaking pace. It begins with the pristine clouds of hydrogen and helium gas, the primordial fuel that has drifted through space for billions of years. The collision's gravitational turmoil compresses these vast clouds, triggering the birth of massive, brilliant stars. These stars are the first actors in the drama, living short, violent lives. Deep within their cores, nuclear fusion forges new, heavier elements, transforming simple hydrogen into the building blocks of complexity, like carbon and oxygen. But this is only the first step. These stellar titans do not fade quietly. They end their lives in cataclysmic supernova explosions, the ultimate act of cosmic recycling. The star is utterly obliterated, and in its final moments, it performs one last crucial service. The explosion blasts all those newly forged elements, the oxygen you breathe, the iron in your blood, out into the surrounding void. This enriched material, now seeded with the essence of a dead star, mixes with the remaining reservoirs of cold gas. The cycle is now complete and ready to begin again. This enriched gas is far more fertile ground for the next generation. When gravity once again pulls a cloud together, it is no longer just simple hydrogen. It is a rich soup of elements, ready to form not just new stars, but also the rocky planets that may orbit them. In a quiet galaxy like our own Milky Way, this process is a slow, stately waltz, taking billions of years. But here in the antennae, the merger has turned the waltz into a frantic, accelerated sprint. The constant gravitational churning ensures that the enriched debris from one supernova is quickly swept up and incorporated into the next collapsing cloud of gas. Star formation, death, and rebirth are happening in rapid, overlapping succession, creating a frenzied ecosystem where the death of one star directly fuels the birth of the next. This is not a linear sequence but a whirlwind of creation, a cosmic loop where every ending is merely a new beginning in disguise. Even the most reliable cosmic signposts are being warped by this galactic turmoil. We rely on certain stars to measure the vast distances of space, and among the most trusted are the Cepheid variables. These are pulsating stars that brighten and dim with a steady, predictable rhythm. Their secret is that this pulsation period is directly tied to their true intrinsic brightness. It is a cosmic heartbeat that reveals its power. By comparing how bright a Cepheid appears from Earth to how bright we know it truly is, astronomers can calculate its distance with remarkable precision. This method is a cornerstone of the cosmic distance ladder, the step-by-step process we use to map the universe. Yet here in the antennae, this reliable heartbeat is being thrown off its rhythm. The environment is anything but stable. A Cepheid variable star here might be bombarded by intense radiation from a nearby supernova cluster, or its outer layers could be stripped by a passing cloud of superheated gas. The relentless gravitational tides, constantly stretching and compressing the space around it, could subtly interfere with the star's own delicate pulsations. Even the sheer density of stars in the superclusters could lead to gravitational interactions that nudge a Cepheid, altering its period. This is a critical problem, because if the star's pulsation period changes, our interpretation of its true brightness becomes flawed. A miscalibrated Cepheid is a broken ruler. If we misjudge its distance, that error cascades through all our measurements of the Antennae Galaxies. We could be wrong about its true size, its total luminosity, and even its distance from us. Astronomers are now forced to act like cosmic detectives, carefully studying each Cepheid they find in the wreckage. They must search for the environmental clues that could be distorting its signal, looking for signs of nearby stellar companions, intense radiation fields, or gravitational disturbances. Only by understanding these anomalies can they recalibrate their cosmic yardsticks, ensuring that the map they are drawing of this colossal collision is not an illusion created by its own violent chaos. The brilliant violence of the antennae does not just emit light, it may also cast a unique kind of shadow across the cosmos. Imagine a distant blazar, a supermassive black hole at the heart of a galaxy billions of light years away, firing a jet of radiation directly toward Earth. This jet is a relentless cannonade of the highest energy photons in the universe, gamma rays. As this torrent of light travels across the universe, it passes through the Antennae Galaxies on its way to our telescopes. The vast clouds of gas and dust churned up by the collision could act like a cosmic filter. When a high-energy gamma ray collides with a lower-energy photon of visible light or infrared radiation floating within these clouds, the encounter annihilates both particles, converting their energy into new particles, an electron and a positron. This process, known as pair production, means that the gamma rays are effectively absorbed. They never make it through to the other side. From our perspective, the antennae would appear to cast a faint, ghostly silhouette against the brilliant backdrop of the distant blazar. This gamma ray shadow would not be a simple dark patch. Its depth and sharpness would be a direct measurement of the total amount of light and matter inside those intervening clouds. A deep, sharp shadow would indicate an incredibly dense and turbulent interstellar medium, packed with the very photons needed to block the gamma rays. A faint, blurry shadow would suggest a more diffuse and porous environment. By mapping this shadow in multiple wavelengths, astronomers could essentially perform a three-dimensional scan of the collision's guts. They could measure the column density of the gas, trace the distribution of interstellar radiation, and understand how the chaotic environment of a galactic merger differs from the calmer medium of a normal galaxy. This hypothetical shadow is more than an absence of light. It is a tool for seeing the invisible structure of a cosmic wreck, using the most energetic light in the universe to illuminate the hidden anatomy of the collision. The invisible gyroscopes at the heart of the collision may be wobbling wildly. If the supermassive black holes are powering jets, those beams of energy are not firing steadily into space. They are likely processing, wobbling like a child's spinning top just before it falls over. This is not a gentle sway, but a violent, chaotic motion driven by the gravitational insanity of the merger. The black holes themselves are not stationary pivots. They are swinging around each other in their frantic binary dance. This motion constantly changes the orientation of their spin axes, and therefore the direction of any jets they emit. The result is a cosmic sprinkler system of unimaginable power, sweeping its furious spray across the surrounding gas clouds. Instead of drilling two neat holes through the galaxy, these processing jets churn the interstellar medium into a frothing maelstrom. They inject colossal amounts of energy and momentum, heating the gas, preventing it from cooling and collapsing to form new stars, and sculpting vast, bubble-like cavities. The patterns they leave behind are not simple lines, but intricate, swirling vortices etched into the fabric of the galaxy. This relentless wobbling ensures that the black hole's influence is felt not just in a narrow channel, but across a much wider volume of space, stirring the entire central cauldron and dictating the rhythm of creation and disruption for light years around. Buried deep within the brilliant chaos of this galactic firestorm are the true survivors, the original inhabitants of the two spiral galaxies. These are the fossil stellar populations, ancient stars that were already billions of years old when the collision began. Their faint, steady light is completely overwhelmed by the dazzling glare of the newborn superstar clusters. Yet they hold the ultimate key to understanding what this system once was. Astronomers face a monumental challenge, akin to trying to hear a single, quiet conversation in the middle of a roaring rock concert. To isolate the fossil light, they must become cosmic detectives, using the subtle language of color and chemistry. Young, massive stars, the brilliant blue giants, are incredibly hot and pour out most of their energy in the blue and ultraviolet parts of the spectrum. They are the flashy newcomers, living fast and dying young. The fossil populations, by contrast, are the old red dwarfs and aging yellow giants. These stars are cooler, and they emit most of their light in the red and infrared wavelengths. By using sophisticated filters on their telescopes to meticulously separate the blue light from the red light across the entire galaxy, scientists can begin to create two distinct maps. One map reveals the frenzied, ongoing starburst regions, painted in brilliant blues and whites. The other map, a ghostly red overlay, reveals the underlying distribution of the ancient stars, the silent bedrock upon which this entire cataclysm is unfolding. This reveals the original galactic skeletons, showing where the old spiral arms and central bulges of the two galaxies were located before they were torn asunder. The chemical fingerprints of these stars provide an even deeper history. By analyzing the spectrum of their collective light, astronomers can measure the abundance of heavy elements like iron. These ancient suns will show a much lower metallicity than the dazzling new stars, proving they formed long ago from a more pristine, less enriched interstellar medium. This fossil record tells a story of two mature, orderly spiral galaxies, each with its own long and quiet history of stellar evolution, that were suddenly and violently thrown off their peaceful course. These silent, ancient suns are the only remaining witnesses to the galaxies that once were, their steady glow a permanent archive of a cosmic past that has been forever erased by the fury of the present. These brilliant boundaries between light and shadow are constantly shifting, where the fierce radiation from newborn stars slams into cold, neutral gas. It carves out a landscape of incredible complexity. These are the ionization fronts, the battle lines where light itself transforms matter, and in the antennae, they are anything but calm. The radiation is so intense that it strips electrons from their atoms, violently ionizing the gas and causing it to glow with an ethereal, energized light. But the sheer chaos of the collision ensures these fronts are never smooth or simple. They are turbulent and fragmented, riddled with intricate filaments, swirling vortices, and delicate, lace-like structures that defy simple geometry. This is not a serene, slow process. It is a frantic, three-dimensional scramble. The radiation pushes outward, but the surrounding gas pushes back, compressed by shock waves from supernova and stirred by the gravitational tides of the merging galaxies. The result is a constantly evolving sculpture of luminous gas, a visible record of the immense pressures fighting for control. What we see as a beautiful, glowing cloud is actually a cosmic battlefield, where the power to create light and the resistance of cold matter are locked in a spectacular, high-energy stalemate. A brilliant supernova suddenly flares in the antennae, a cosmic firework signaling the death of a star. Yet when astronomers scramble to look at archival images of that exact spot, they find a void. There is no sign of a massive, unstable star that should have been there, the expected progenitor of such a violent explosion. This is the mystery of the missing supernova progenitors, a cosmic detective story where the prime suspect has vanished from the scene. Our understanding of stellar evolution is built on a clear timeline. Truly massive stars, the kind that end their lives as core collapse supernova, are supposed to be brilliant, blue, and short-lived. They burn through their fuel in only a few million years, a blink of an eye on the cosmic scale. So when one explodes, we expect to see evidence of a young, hot, massive star in the pre-explosion data. But in the frantic stellar nurseries of the antennae, that is often not the case. The progenitor stars are conspicuously absent, forcing a difficult question. Are our telescopes simply not powerful enough to pick out a single star amidst the dazzling glare of a superstar cluster? Or is something more fundamentally wrong with our stellar models? The answer may lie in the extreme social life of stars in this crowded environment. The antennae is a galactic mosh pit where stars are packed together with incredible density. In such chaos, close encounters and direct collisions are not just possible, they are inevitable. This opens the door to an exotic explanation: stellar mergers. Imagine two older, lower mass stars, perhaps red giants, that have been orbiting each other for billions of years. The gravitational turbulence of the merger could destabilize their orbit, drawing them into a fatal spiral. They collide, merging into a single, rejuvenated star that suddenly gains a new lease on life, and a new, violent destiny. This newly merged star would be a Frankenstein's monster, its outer layers a tangled mess, and its core suddenly flooded with fresh fuel. This influx can trigger a renewed and accelerated bout of nuclear fusion, pushing the star toward a rapid and unexpected collapse. It would explode as a supernova, but its pre-merger identity would have been that of two older, quieter stars, completely unlike the young behemoth we expected to find. Another possibility involves mass transfer in tight binary systems, where one star steadily siphons material from its companion. This process can also dramatically alter a star's life cycle, making it appear younger and more massive than it truly is, and ultimately leading to an explosion that seems to come from nowhere. The missing progenitors in the antennae are therefore a direct challenge to the textbook life cycle of a star. They suggest that in the ultimate cosmic pressure cooker, the rules can be rewritten, and a star's death can be triggered not just by its internal clock, but by a violent encounter with a neighbor. This ongoing collision is generating a hidden sound that will one day fill the cosmos. Long after the light from the Antennae Galaxies has faded, the echoes of its violence will persist as a faint, persistent hum woven into the fabric of spacetime itself. This is the gravitational wave foreground, a low-frequency rumble created not by one single event, but by the combined chorus of countless cosmic mergers happening within the wreckage. The primary sources of this hum are the compact binary systems forged in the chaos, pairs of neutron stars or stellar mass black holes locked in a final, intimate dance. The galactic collision has created a perfect environment for these pairs to form and be driven together. As these incredibly dense objects orbit one another, they lose energy by radiating gravitational waves, those ripples in spacetime predicted by Einstein. This energy loss causes their orbits to slowly decay, tightening their spiral over millions of years until they finally collide in a flash of invisible energy. A single such merger produces a brief, crescendoing chirp, but the Antennae Galaxies are home to thousands, perhaps even millions, of these binary pairs, all at different stages of this slow-motion plunge. Their individual chirps overlap in time, creating a continuous stochastic background. It is the cosmic equivalent of a vast forest filled with crickets, where the chirp of any single insect is lost in the overwhelming collective drone of the entire population. This background hum is too faint and too low in frequency for our current observatories like LIGO to detect. It requires a new kind of ear, a space-based gravitational wave observatory that can listen for the slow, universe-spanning undulations. Future missions will tune into this frequency band, and when they do, the Antennae Galaxies will be a prominent voice in that chorus. The legacy of this collision is therefore not just a new galaxy, but a permanent vibration, a note added to the universe's silent, resonant song. Woven through the glowing gas and dark dust of the antennae are intricate, ghostly tendrils that shine with a very specific kind of light. These are polycyclic aromatic hydrocarbon nebulae, vast clouds of large organic molecules that fluoresce when bathed in the harsh ultraviolet radiation from newborn stars. The name is complex, but the concept is beautifully simple. Picture the structure of a soccer ball made of carbon atoms. Then imagine flattening that ball into a flat hexagonal sheet, like a tiny piece of graphene or a microscopic flake of charcoal. Now, link many of these sheets together into larger, more complex molecules. This is a polycyclic aromatic hydrocarbon, a PA. They are essentially the fundamental building blocks of soot, but here, in the chaos of the galactic collision, they exist on an interstellar scale. These molecules cannot withstand the direct, brutal UV radiation in the heart of a superstar cluster, where that high-energy light would tear them apart. Instead, they thrive in the transition zones, the photodissociation regions that form a protective boundary between the intensely illuminated gas and the cold, dark clouds. It is in these regions that the ultraviolet light is just strong enough to energize the pH molecules, causing them to vibrate and emit their own characteristic glow in the infrared part of the spectrum. This creates a delicate, luminous filigree that traces the intricate frontiers where light and shadow meet, Their abundance here is a direct result of the collision's creative fury. The constant cycle of star birth and supernova death has flooded the interstellar medium with carbon, the raw ingredient for these molecules. The same violent processes that forge stars are also manufacturing these complex organic compounds in staggering quantities. And this is where the story becomes profoundly relevant to us. Polycyclic aromatic hydrocarbons are considered crucial prebiotic molecules. They are the stepping stones, the fundamental scaffolds upon which the even more complex chemistry of life could potentially be built. The Antennae Galaxies are not just building stars and planets. They are filling the cosmic landscape with the very seeds of organic chemistry, proving that the ingredients for life are a natural byproduct of the universe's most violent and creative acts. These galactic components are not moving in a synchronized dance. In the chaotic heart of the antennae, the stars and the gas often travel on wildly different paths, as if obeying two separate sets of cosmic laws. This strange divorce of motion is known as kinematic decoupling, and it reveals a fundamental difference between how matter behaves in a collision. The countless stars are essentially solitary voyagers in a vast emptiness. The spaces between them are so immense that when galaxies collide, the stars themselves almost never physically crash into one another. They are collisionless, their paths altered only by the smooth, large-scale pull of gravity. They can retain the memory of their original orbits for a long time, swinging through the merger on trajectories established before this cosmic wreck began. The gas, however, is a different story entirely. It is not a collection of isolated points, but a continuous, turbulent fluid. When these two gigantic rivers of interstellar gas slam together, they do not pass through each other ghost-like. They collide. The countless atoms and molecules smash into one another, creating immense shock waves and friction. This violent interaction robs the gas of its energy, causing it to slow down and lose its momentum. As it bleeds off this energy, it can no longer maintain its previous, wider orbit. It begins to fall away from the stellar flow, decoupling from the stars and spiraling inward toward the gravitational center of the merger. You can envision this as a cosmic traffic jam within a swirling hurricane. The stars are like cars that can somehow pass through each other, maintaining their speed and direction as they are guided by the road's curves. The gas, however, is like a thick, dense fog that has been caught in the storm. The fog banks collide and pile up, losing their forward momentum, and are drawn inexorably toward the eye of the hurricane. The result is a profoundly misaligned system. Astronomers mapping the velocities see one pattern for the stars, perhaps a remnant of an old, rotating disk, and an entirely different, chaotic flow for the gas, funneling inward to fuel the central starburst. This decoupling is not a minor detail. It is the central mechanism that feeds the engine of creation. The gas's inability to resist the pull of friction and gravity is what delivers the raw fuel to the galactic core, directly enabling the firestorm of star birth that defines the entire collision. The stars and the gas, once partners in a graceful spiral, are now following separate destinies, their divorced motions writing the next chapter in the life of this new galaxy. Every brilliant cloud of gas in the antennae has its own unique temperature, a hidden thermal state we can read like a cosmic thermometer. Astronomers do not plunge a probe into these distant fires. Instead, they decode the very light the gas emits. The secret lies in the ratio of specific spectral lines, the unique fingerprints of elements like oxygen and nitrogen. A cloud of gas that is relatively calm and cold will produce one particular pattern of these lines. But take that same cloud and heat it to millions of degrees with a supernova shockwave, and the pattern shifts dramatically. The relative strengths of the lines change, providing a direct and precise measurement of the gas's thermal energy. This reveals a stunning thermal tapestry woven across the collision. Vast regions near the superstar clusters are scorching, their gases heated to blistering temperatures by the relentless ultraviolet radiation from newborn stars. Elsewhere, the expanding shells of ancient supernova remnants are mapped as spheres of intensely hot, shocked material. Yet, just next to these infernos, deep within the dark pillars of creation, pockets of gas persist at temperatures only a few tens of degrees above absolute zero. These extreme temperature differences are the engine of the system. The hot, high-pressure gas expands violently, slamming into the cold, dense clouds. This collision of thermal states creates immense shock fronts that trigger the next round of gravitational collapse, seeding the birth of future stars. The cosmic thermometer does not just show us where things are hot or cold. It reveals the pressure fronts and energy flows that are actively sculpting the galaxy's future, one violent temperature gradient at a time. Out in the lonely expanse of the tidal tails, the debris is fighting back. Those vast rivers of stars and gas are not just passive streams. They are actively forming their own gravitational centers. Astronomers have identified dense, bright knots within these antennae, colossal clumps of matter that are so massive they have achieved a stunning degree of independence. These are the tidal dwarf galaxy candidates, and they represent one of the most profound ideas to emerge from this collision. Could the wreckage of two galaxies actually give birth to entirely new, smaller galaxies? Each candidate is a miniature cosmos in the making, a collection of billions of stars and vast clouds of gas that has condensed out of the tidal material. They are not simply clusters, they are true galactic embryos, possessing their own self-gravity, their own reservoirs of cold gas, and their own ongoing star formation. They are forging their own destinies, far from the chaotic core that created them. This process turns our understanding of galaxy formation on its head. We have long thought that large galaxies grew from the bottom up, with small primordial clumps merging to build giants. But here we are witnessing the opposite, a top-down process where a giant galaxy shatters, and from its pieces, new small galaxies may be born. It is galactic fragmentation, a cosmic example of destruction directly enabling a new wave of creation. Yet a critical question hangs over these fledgling systems. Will they survive? Their future is a delicate tug-of-war between two powerful forces. Internally, their own gravity is trying to hold them together, to bind their stars and gas into a permanent, stable structure. Externally, they are still attached to the main merger by a tenuous umbilical cord of stars and dark matter, a gravitational link that constantly tugs at them. The outcome depends entirely on their mass. If a tidal dwarf candidate has gathered enough material, if it is truly a heavyweight, its self-gravity may be strong enough to resist the pull. It could remain a distinct, orbiting satellite galaxy for billions of years, a permanent offspring of the violent merger. But if it is too lightweight, the gravitational pull from the main galactic body will eventually prove too strong. Over hundreds of millions of years, it will slow down, its orbit will decay, and it will be drawn back into the fiery embrace of the parent galaxy. Its stars would then be reassimilated, its gas fueling future rounds of star formation. Observing these candidates today is like watching a baby bird that has just been pushed from the nest. We are witnessing their first, frantic attempts to fly, and we do not yet know which of them will soar and which will fall. Their struggle for existence adds yet another layer of drama to this cosmic collision, proving that even in the farthest flung debris, the battle between creation and destruction is still being waged. Even the dust itself tells a strange new story in this collision. The fine, dark grains that drift through the interstellar clouds of the Antennae Galaxies are not like the familiar dust of our own Milky Way. In our quiet galactic neighborhood, dust grains are typically a mix of silicates and carbon-based compounds, formed over eons in the calm atmospheres of aging stars. They are weathered and processed through gentle cycles. But here, the rulebook has been thrown out. The extreme violence of the merger is fundamentally altering the very nature of these tiny particles. The primary culprit is shattering. In the turbulent maelstrom, where supersonic shock waves from supernova and colliding gas clouds ripple through space, dust grains are not merely nudged. They are slammed together at phenomenal speeds. These high-velocity collisions do not just stick particles together, they blast them apart, shattering larger grains into a fine, microscopic mist. This process dramatically skews the size distribution of the dust, flooding the environment with an overabundance of exceptionally small grains. Think of it as the difference between a beach of fine sand and one covered in coarse gravel. A beach of fine sand has a much greater total surface area. In the antennae, this is exactly what happens. The collective surface area of all the dust particles skyrockets, and this has a profound effect on how the dust interacts with light. These tiny grains are superb at absorbing the fierce, high-energy ultraviolet radiation pouring from the young star clusters. They heat up rapidly, but because they are so small, they cannot hold that heat for long. They re-radiate it almost immediately, but at a much different wavelength, primarily in the mid-infrared. This gives the entire interstellar medium a unique thermal signature, a pervasive, warm glow that would be absent if the dust were composed of larger, more robust grains. At the same time, in the coldest, darkest recesses of the gas clouds far from the stellar firestorms, another transformation is occurring. Here, the shattered grains act as seeds. Atoms and molecules of water, carbon monoxide, and other volatile substances, which would normally float as a gas, find a solid surface to cling to. They freeze onto the dust, building up mantles of ice. A grain that might have started as a speck of silicon is now a complex core mantle structure, a tiny icy snowball drifting in the void. This icy coating completely changes how the grain behaves. It becomes more efficient at sticking to other grains during low-speed collisions, potentially building larger aggregates. It also alters the way it scatters and absorbs light, particularly in the infrared. The presence of these ice mantles creates specific absorption features in the spectra of background stars, telling astronomers not just that dust is there, but precisely what it is dressed in. This anomalous dust is far from a minor detail. It directly impacts the most fundamental process in the galaxy, the birth of new stars. Dust grains are the primary catalysts for the formation of molecular hydrogen, the essential fuel for star formation. A grain's size and surface composition determine how efficiently it can facilitate this chemistry. Furthermore, dust provides the shielding necessary for fragile molecules to form, protecting them from destructive ultraviolet radiation. The strange, shattered, and ice-coated dust of the antennae is therefore an active participant in the cosmic drama, a substance transformed by violence that now goes on to shape the very future of the galactic merger. The brilliant tapestry of the antennae is not woven with a steady hand. Across its chaotic expanse, star formation ignites in a series of brilliant, unpredictable flashes, a process so random it is described as stochastic. This is not a gentle, galaxy-wide drizzle of new suns, but a celestial fireworks show where a few massive clusters fire off at random, their collective roar drowning out all other sounds. The overall rate of star birth for the entire system is not a smooth average. It is a statistic dominated by these rare, colossal events. Picture a vast, dark field scattered with firecrackers. Most of the time, a few small ones pop here and there, creating a faint, sputtering light. But then, without warning, a single massive bundle of explosives detonates, flooding the entire landscape with a blinding, momentary glare. That single, random blast contributes more light to the entire night than all the smaller pops combined. This is precisely what happens in the antennae. A handful of superstar clusters, each containing the mass of millions of suns, can form in a spectacular, localized burst. For a brief cosmic moment, that one region outshines everything else, single-handedly driving up the measured star formation rate for the whole galaxy. This stochastic nature means the future of the antennae is not preordained. Its evolution is not a smooth curve on a chart, but a jagged, unpredictable line, shaped by the random timing and location of these monster clusters. The legacy of this collision will be written by a cosmic lottery, where a few lucky, intensely bright winners determine the final chemical and structural makeup of the new galaxy rising from the wreckage. These ghostly rings of light may be the closest thing we have to a cosmic replay button. Long after a supernova's initial flash has faded in darkness, its light can still be traveling, reflecting off vast, distant walls of interstellar dust. We call these apparitions light echoes, and finding one in the antennae would be like receiving a delayed message from the collision's violent youth. Imagine a single, brilliant supernova that exploded a century ago. Its light rushed outward in all directions, a sphere of radiation expanding at the speed of light. The first wave traveled directly to Earth, and astronomers of the past recorded a brilliant new star where none had been before. But other photons from that same explosion took a longer path. They raced past us, continuing into deep space until they slammed into a colossal, dark cloud of dust hundreds of light years away. The dust did not absorb this light, it scattered it, reflecting it back toward us like a cosmic mirror. Now, 100 years later, that reflected light finally arrives at our telescopes. We see it not as a point, but as a faint, expanding ring on the sky, a perfect circle that grows larger year after year. This echo is a direct snapshot of the original event, a time capsule containing the precise spectrum and color of that ancient stellar death. In the Antennae Galaxies, where supernovae have been detonating for millions of years, the potential for such echoes is immense. A single, perfect ring would allow astronomers to perform forensics on a star that died long before the merger reached its current chaotic state. By analyzing its light, they could determine exactly what kind of star exploded, its chemical composition, and the precise mechanics of its death. It would be a window into the merger's past supernova rate, revealing whether these stellar explosions were even more frequent in earlier stages of the collision. The search for these phantom rings is a patient one, requiring telescopes to compare images of the same region taken years or even decades apart, looking for any subtle, expanding ghost in the machine. To find one would be to catch the antennae in a moment of unintended transparency, allowing us to look back in time and watch the echo of a single, cataclysmic note in the galaxy's long, violent symphony. Even the stability of a star's closest companion is not guaranteed in this chaos. The gravitational tides coursing through the Antennae Galaxies act like a cosmic wrecking ball on binary star systems, those pairs of suns locked in a mutual orbit. For wide binaries where the two stars are separated by a vast distance, the relentless and uneven pull of passing star clusters and dark matter clumps can be catastrophic. Imagine two dancers holding hands, spinning slowly in a vast, empty ballroom. Suddenly, the room is flooded with a swirling, chaotic crowd. Other dancers jostle them, pulling and tugging at their arms from all directions. Their grip is broken, and they are flung apart, lost to each other forever in the crowd. This is the fate of countless wide binaries in the antennae. The gravitational perturbation from a close encounter injects extra energy into their system, giving one or both stars enough of a kick to achieve escape velocity. They drift apart, becoming solitary suns on independent, lonely paths through the galactic wreckage. But for other binaries, the outcome is the opposite. If their initial orbit is tighter, the same chaotic forces can compress it. The gravitational shock does not tear them apart, but instead forces them into a closer, more frantic, and highly elliptical dance. Their once stable circular path becomes a strained oval, a roller coaster orbit where the stars swing extremely close together before hurtling to their farthest separation. This dramatic reshaping of stellar relationships has profound consequences for the galaxy's future. A binary system forced into a tighter embrace becomes a prime candidate for a spectacular death. As the stars draw closer, one can begin siphoning material from its companion, a process that can lead to classical nova or even trigger a Type Ia supernova, the kind used to measure cosmic distances. In other cases, if one of the stars is a dense remnant like a neutron star or a black hole, this forced proximity allows it to feast on its partner's gas, igniting as one of those brilliant, mysterious, ultraluminous X-ray sources we see scattered across the galaxy. The disruption of these simple stellar partnerships is therefore a direct factory for the most violent and energetic phenomena in the collision, proving that here, even the most fundamental bonds between stars are rewritten by gravity's relentless hand. The interstellar medium of the Antennae Galaxies churns with its own violent weather. Vast, dark molecular clouds act as cosmic high-pressure systems, their immense gravity crushing gas into dense, frigid knots where future stars lie dormant. These are the calm before the storm, the celestial mountain ranges where pressure silently builds. But surrounding them are the galactic equivalents of hurricanes, colossal low-pressure zones carved by ancient supernovae. These are the superbubbles, cavities of million-degree gas blown clear by thousands of sequential stellar explosions. Within these voids, the interstellar air is thin and hot, a permanent high-pressure front pushing relentlessly against the colder, denser clouds at their borders. This constant clash of thermal states generates supersonic shock fronts, the squall lines of this cosmic climate, where gas is compressed and star formation is triggered. The most violent storms are the stellar winds screaming from newborn massive stars. These are not gentle breezes, but a constant hypersonic gale of charged particles that sandblast the surrounding space, sculpting pillars and eroding gas clouds. This entire chaotic climate is a self-regulating engine, where the death of one generation of stars in supernova hurricanes clears space and compresses gas to birth the next. The forecast for the antennae is never calm. It is a perpetual, violent storm of creation and destruction, a weather pattern written in fire and gravity. A strange cosmic blind spot obscures our view of the Antennae Galaxies. The universe's expansion is stretching their light, shifting it toward the red end of the spectrum, and this specific redshift places some of their most vital signals in a problematic zone. For astronomers, this creates a redshift desert, a barren stretch of the electromagnetic spectrum where the atmosphere itself becomes an enemy. Our own air is filled with water vapor and other molecules that greedily absorb certain infrared wavelengths, creating an opaque wall that ground-based telescopes simply cannot see through. This means that some of the most important spectral lines, the unique fingerprints of elements like oxygen and carbon that tell us about the temperature and motion of the gas, are lost in this atmospheric fog. It is as if we are trying to listen to a symphony from outside a concert hall, but the most critical instruments are playing in a key that the walls completely muffle. To hear this missing music, we must rise above the atmosphere. Space-based observatories like the legendary Hubble and the revolutionary James Webb Space Telescope are our only ticket into this silent zone. They operate in the vacuum of space, far above the blanket of air that cripples our ground-based view. With their infrared eyes, they can detect the faint, stretched light that holds the secrets to the antennae's violent star formation and chemical enrichment. This redshift desert is a stark reminder that our understanding of the cosmos is limited not just by the power of our instruments, but by the very air we breathe. It forces us to become cosmic explorers, launching our eyes beyond the sky to fill in the blank spots on the map of this magnificent collision. The chaotic plasma surging through the antennae is generating a current of cosmic proportions. This is the cosmic battery effect, a fundamental process where the galaxy itself becomes a colossal electrical generator. Imagine the vast, magnetized rivers of hot gas, stirred by the collision, flowing like a titanic conductor through the galaxy's own magnetic fields. When a conductor moves across a magnetic field, it induces an electrical current. This simple principle, the same one that powers a bicycle dynamo, is operating here on an almost unimaginable scale. In the turbulent environment of the antennae, this effect is amplified to its absolute limit. The supersonic collisions between gas clouds, the violent outflows from supernova, and the churning motions of the entire merger create a chaotic, fast-moving plasma. This plasma is a sea of charged particles, a perfect conductor for this natural dynamo. As it surges across the invisible magnetic field lines woven through the galaxy, it generates immense electrical potentials. These are not gentle trickles of electricity, but vast, organized currents flowing through the interstellar medium. What powers these bizarre currents? The energy source is the kinetic fury of the collision itself. The gravitational energy released as the two galaxies smash together is converted into the violent motion of gas, and this motion is then transformed, via the cosmic battery, into raw electrical power. This electrical energy does not simply dissipate. It becomes the hidden driver for some of the most unusual emission phenomena in the entire system. These currents can channel their energy into accelerating particles to nearly the speed of light, creating the intense synchrotron radiation we detect as radio waves that outline the galactic wreckage. They can heat pockets of gas to extreme temperatures, contributing to the brilliant, diffuse X-ray glow that permeates the collision. In the most extreme environments, like the regions surrounding the ultraluminous X-ray sources, these galactic-scale currents could even be feeding the very processes that allow black holes to shine beyond their theoretical limits. The Antennae Galaxies are not just a scene of gravitational and thermal violence. They are a live wire, a short-circuiting celestial machine where the motion of an entire galaxy is being transformed into a storm of raw electricity. Buried deep within the light of every star here lies a ghost from the dawn of time. Before this collision ever began, before the two spiral galaxies even fully formed, the very first generation of suns may have lived and died within them. These are the hypothetical population 3 stars, the universe's original pioneers. They were not like the stars we know today, born from the pristine, uncontaminated clouds of only hydrogen and helium that filled the young cosmos. They had no heavy elements to help them cool and fragment. This meant they grew to monstrous proportions, reaching masses hundreds of times that of our own sun. Their lives were brilliant, violent, and tragically short. They burned through their nuclear fuel in only a few million years, a fleeting flash on the cosmic timescale, before exploding in cataclysmic supernova or collapsing directly into black holes. Their deaths, however, were their most important contribution. Within their cores, nuclear fusion forged the universe's first heavy elements, the very first atoms of carbon, oxygen, silicon, and iron. In their final moments, they scattered these elemental seeds across the embryonic galaxies. This first pollution run was the most crucial event in the chemical history of the Antennae's ancestors. It transformed the cosmic gas from a simple soup of primordial elements into a more complex, fertile medium. Every subsequent generation of stars, including the ancient fossil stars we see today and the brilliant new ones being born now, owes its very existence to that initial enrichment. The iron in your blood and the calcium in your bones can be traced back through countless stellar generations, but the very first atoms of those elements were likely forged in the hearts of these long-vanished giants. We will never directly see a population 3 star, as the last one died billions of years ago. Yet, their legacy is woven into the fabric of this entire collision. When astronomers measure the chemical composition of the Antennae's gas and its oldest stars, they are looking for a specific, faint signature, an elemental pattern that points to a single, rapid enrichment event long, long ago. Finding that fingerprint would be like discovering the grave of a mythical founder, confirming that the violent beauty we see today is built upon the ashes of the very first stars. These violent motions are powering a cosmic generator deep within the wreck. The chaotic churning of gas and stars in the Antennae merger is acting as a colossal dynamo, amplifying weak magnetic fields into powerful, organized forces that thread the entire collision. This is not a machine made of wires and magnets, but a natural engine that operates on the grandest of scales. The process begins with even the faintest, most primordial magnetic field, a whisper of a force left over from the early universe. As the vast rivers of superheated plasma swirl and shear against each other, they stretch and twist these weak field lines. Picture a pot of thick soup on a simmering stove. If you stir it slowly with a spoon, you might create a gentle swirl. But if you whip it into a frantic vortex, the liquid folds over on itself, stretching and intensifying any tiny currents within it. The Antennae merger is that pot, stirred not by a spoon, but by the unimaginable forces of a galactic collision. The differential rotation, where some parts of the gas cloud move faster than others, and the sheer turbulence from supernova shocks and stellar winds, all work together to wind up the magnetic field like a coiled spring. This dynamo effect transforms a disorganized magnetic whisper into a roaring, structured presence. The energy for this amplification is stolen directly from the kinetic motion of the gas itself. The gravitational violence of the collision, which sets the entire system churning, is ultimately converted into magnetic energy. This process is fundamental. It is the very mechanism thought to generate the magnetic fields we find in all galaxies, from quiet spirals like our own to the most chaotic ellipticals. The Antennae offers us a rare, accelerated view of this process in its most extreme form. We are witnessing a galactic dynamo running at its absolute limit, showing us how the invisible magnetic skeletons of all galaxies are forged in the fires of cosmic turmoil. Our own fleeting existence prevents us from seeing this collision as it truly is, a continuous and dynamic event. We are granted only a single, frozen frame from a film that runs for hundreds of millions of years. Every structure we have explored, from the tidal tails to the warped magnetic fields, is locked in a state of imperceptible motion. The galaxies are not static sculptures. They are caught in the middle of a verb, an action of unimaginable slowness. If we could compress 1,000,000 years into a single second, the entire scene would erupt into a frantic, swirling dance. The vast tidal tails would writhe like the tentacles of a deep-sea creature. The superstar clusters would drift and jostle for position, and the central black holes would visibly spiral inward on their decaying orbit. But our human timescale renders this cosmic ballet motionless, a colossal still life painted across the void. This time dilation of perception creates a fundamental illusion. We see a snapshot of chaos and assume it is the permanent state of the system, when in reality, we are witnessing a single moment in a continuous transformation. The brilliant pillars of creation we marvel at are not permanent monuments. They are temporary scaffolding that will be eroded away in a celestial heartbeat. The runaway stars we have tracked are not frozen in their escape. They are in the midst of a journey that will take them across the intergalactic abyss. Our entire understanding of the antennae is built from this one static perspective, forcing us to use physics and computer simulations to animate the frozen image, to wind the cosmic clock forward and backward to understand the story of which this is only one page. The brilliant, chaotic firestorm of the Antennae Galaxies is not a permanent state, but a fleeting, spectacular chapter. Billions of years from now, this cosmic wreck will settle into a final, profound silence. The two mangled spirals will have fully coalesced into a single, massive entity, a smooth, featureless elliptical galaxy. The long, graceful antennae, those iconic tidal tails, will have faded from view, their stars either drawn back into the new galactic core or scattered so far apart that the streams simply dissolve into the darkness of intergalactic space. The furious burst of star formation, which once illuminated the chaos, will have long since burned out. The raw fuel for this fire, the vast clouds of cold hydrogen gas, will be entirely exhausted, consumed in the final great starburst or blown away in the void by relentless galactic winds. Without this fresh fuel, the stellar nurseries will go dark, and the last of the brilliant blue giant stars will have lived out their short, violent lives, exploding as supernova or collapsing into dark remnants. What remains is a population of aging stars, the long-lived red dwarfs and cooling yellow giants, that will slowly, inexorably burn through their remaining fuel over trillions of years. This new galaxy will glow with a calm, reddish hue, a stark contrast to the blue-white ferocity of its youth. It becomes what astronomers call a red and dead galaxy, a quiet celestial retirement home where stellar births have ceased, and the primary activity is the slow, graceful aging of countless ancient suns. The central supermassive black holes will have finally merged, their gravitational waves having rippled out across the universe, and will now lie dormant at the heart of this serene giant, a sleeping monarch with no more subjects to rule. This elliptical galaxy will stand as a permanent monument, a fossilized testament to the incredible violence of its birth. Every one of its stars carries the chemical imprint of that ancient collision, and its very shape is the direct result of that gravitational turmoil. The beautiful, structured spirals that once were are gone forever, erased by a slow-motion impact that transformed chaos into a lasting and silent order. So much more than a distant spectacle, this journey through 50 strange phenomena reveals the Antennae Galaxies as a cosmic crucible. Here, the fundamental laws of physics are not just broken, they are rewritten in the fires of creation and the voids of destruction. We have witnessed stars flung into the void, black holes locked in a death spiral, and entire galaxies being forged from the wreckage of their predecessors. This is not a static picture. It is a living laboratory where the universe conducts its most extreme experiments in real time. And this grand collision holds a profound mirror to our own future. The serene spiral of our Milky Way is living on borrowed time, destined for a similar, spectacular dance with the Andromeda Galaxy billions of years from now. The chaos we see unfolding in the antennae is a preview of our own celestial fate, a reminder that the cosmos is in a constant, beautiful state of upheaval. We have walked through 50 of its strangest secrets, from stellar ghosts to phantom dark matter clumps. Now we want to hear from you. Which of these phenomena reshaped your understanding of the universe the most? Was it the runaway stars, the invisible magnetic architecture, or the very real possibility of new galaxies being born from the debris? Share your thoughts, and the next time you look up at the night sky, remember the invisible, violent, and utterly magnificent ballet unfolding in the darkness above.